Hello everyone, we're going to look at 6.3a today. We're just going to look at basic binomial functions. Let's go. By the way, I don't own this PowerPoint. I don't say enough. I'm using it. Please don't report me. Alright, today we're going to learn about how to tell whether or not something's binomial, how to interpret and calculate binomials. For B, we'll look at find the mean and standard deviation of binomials, and for C, we will look at geometric distributions. Alright? Cool. So, how do we know something's a binomial function, a binomial setting? Like, how are we going to know that we're using binomial stuff? Well, we're going to use something called bins. Bins, binomial, same thing. So, come on. All right. So, bins. B, I, N, S. The first thing you ask yourself when you're looking at a situation to determine whether or not it's binomial is it success, failure? Is it binary? Binary means two. Are there two options? You either win or you lose. You either make the shot, you don't make the shot. You pass the test, don't pass the test. You can't do this if you're doing like, what's probably they get an A or B and not a C, D, or E. Unless you define getting an A and B as success, C, D, and E as failure. Okay? So all depends on how you word the problem. Is it independent? Do the trials depend on each other? If each trial doesn't matter, it means it's a binomial. Is there a set number of trials? Like he's going to take 10 shots. You're going to grab 20 students. Has to be fixed in advance. And does the probability of success, is it the same on every trial? If you're like, I'm going to flip a coin 10 times, heads is success, tails is failure. Every time you flip it's independent, and every time you flip it, it's a 50-50. That would pass. Watch, it's going to do the same thing. Pow! Look at that. Whoa, gee golly. Alright. We will be going through this in the big ideas in class. Alright. Get you in. So let's take a look at an example. Let's say genes you get from each parent is independent from each other. Each parent has a probability of 0.25 of having type O blood, and those parents have 5 children. Count the number of children with type O blood. Let's check bins. Is it binary? Yes. We'll denote success is having type O blood, and failure is not having type O blood. Okay. Is it independent? Yes. Each child's genetics are independent of each other. Just because one kid has it doesn't mean the other kid won't. Is there a set number? Yeah, we're doing 5 trials. Is the probability 0.25 every time? Yes. This is a binomial setting. Bins gets passed. Let's look at another one. Suppose you have a deck of cards, and you turn over the first 10 cards one at a time, and aces is going to be what you record. Is it binary? Yes. Ace is success, not ace is failure. Independent? No. If the first card you get is an ace, it will change the probability of each next card. If it's not an ace, it will change the probability. Because the probability of the first time you throw down a card is an ace is 4 over 52. The next time you throw it down, if you don't get an ace, is 4 out of 51. So the probability changes. It depends on the other. Fails independent, not binomial setting. Now we're going to do it again. Turn over the top card, put it back, shuffle. Repeat until you get an ace. Is this binomial? Binary, yes. Ace is success, non-ace, not a success. Independent, yes, because you replace, so it stays the same each time. Is there a set number? No, because you're flipping until you get an ace. You need a set number of trials. Now, if you had said, I'm going to flip out, I'm going to do it 10 times and count how many aces, that would have been good. Now, if the binomial setting passes, then x is a binomial random variable. Okay? Alright, and the distribution is a binomial distribution. Alright, we good? Now, you don't have to write this down. You know who I'm talking to. So, the binomial distribution is what we're going to use to find the probability of how many successes given a number of trials. Now, if we have binomial setting and we want to know what's the probability on that first example that 3 out of the 5 children are type O blood, we're going to use binomial distribution. All right? Get set number, how many successes? Let's look at it. What's the probability exactly 1 has type O blood? We use a formula. Oh, Moby. All right. The formula is well, think about it this way. There's 5 different ways to have one child with type O blood. You could have O, nano, 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 O, nano, O, nano, 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 nano. I mean, you could have O, not O, not O, not O, not O. You could have not O, O. Right? There's 5 different ways you could have had kids. 5 different combinations that you could have had one kid with O. Now, what's the probability that one kid had type O blood? 0.25. 0.25 to the first power. What's the probability? Sorry, I have to do this. My back. I'm getting old. What's the probability then that the other 4 don't? Well, the complement's 0.75 to the 4th. So I got 0.3955. Now, I like this way. It makes sense to me, but there's other ways to do it as well. I'm going really fast. I'm sorry. We will go through this in more detail in class. Here's the formula that you'll use. Sorry guys, I had people come in my room. So it's number of ways to get k successes, number of successes to the k, times the failure probability to the n minus k. So like, let's say I'm a 20% free throw shooter. I shoot 5 shots. I want to know probability of making 2. Well, 5 choose 2, there's, oh geez, I forget how many ways. I think there's 10 ways. I do 10 times my 0.8 to the 2 times, that's a bad example. Let's just keep going. Now, instead of listing out all the different combinations there is a formula for it. And that's n over k. Your calculator also does this. It's called n choose k. And if you're looking to find this in your calculator and the factorials, you hit math, and you go over to probability, and you see there's an they call NCR. I did n choose k, and there's also a factorial. Math, probability. Okay. So this is n choose k. Given we have 100 things and we're choosing 6 of them, how many different ways are there for that to occur? That's the formula for it. I've never seen you have to do it that way. If you have questions on that, I will go over that in more detail in class. All right? But just know that's n choose k, and know that you can use a calculator for it. And the bigger thing is going to be to interpret this. All right? Oh, it is not a fraction. Not a fraction! All right, cool. All right. Oh, geez. So now this is our new formula. Again, this formula has come up a lot. The formula, remember, this is, if you're doing your calculator, it'll be NCR times P to the K, where P is the probability of success, K is the number of successes, times your complement to P, 1 minus P, to the number of trials minus k. So it's how many times you failed to the power of what your chances of failing times probability of success, how many successes you had, times how many different ways you could do it. Alright? Again, rapid fire. I'm sorry. You can pause it, learn it, love it. Let's try it. Learn it, love it, try it. Alright, hold on, I have all these notes. Everywhere I go, I'm in over my head, over my head. I don't own that song either. Alright, let's look at this one. Alright, suppose, same thing, each probability has 0.25 of getting O. What's the probability that x equals 3 this time? So what's the probability that we get 3 children on this? Okay. So I have 5 trials, right? So my number of trials is 5. My k is 3, because I'm looking for 3 successes. Agreed? I'm doing p of x equals 3. My probability of success is 0.25, because we're counting type O as success. My probability of failure of not succeeding is 0.75. Let's plug in. So I'm going to do 5 choose 3 times 0.25 to the success rate times 0.75, my fail rate, to the 5 minus 3. Right? And I'm going to plug that in. And according to my calculations, I got, this is 10, and I got 0.088. So to interpret, there's an 8.8% probability that exactly 3 of the 5 children have type O blood. Let's check it. Let's see what they got. They got the same thing. I'll check. Alright, let's try another one. Last example. Same problem. 0.25 type O, 5 children. Should they be surprised? Should that dad go talking around to some other dads if more than 3 of their children are type O blood? So, what are we trying to find here? We want to know the probability that x is greater than 3 and see if it's weird. Okay? So, what that means is I'm going to find the probability of x equals 4 and add it to the probability of x equals 5, right? Because 5 plus 4, 5 and 4 are the 2 values above 3. So I have to find each. So everything's going to be the same as before, but my k is now 4. And my k is now 5. Right? So I'm going to do 5 choose, well, not a fraction. Calm down. 5 choose 4 times 0.25 to the 4 times 0.75 to the 5 minus 4, which is 1. Right? I'm going to find that. I'm going to add it to 5 choose, not a fraction. 5 choose 5 times 0.25 to the 5 successes now times 0.75 to the 5 minus 5, which is 0. And when I do this, I got 0.016. Uh-oh. That's pretty low. Awkward conversations there. That means there's a 1.6% probability of having 3 or more, or having more than 3 children with type O blood with these 2 parents. Let's see if the book agreed. They did. Oh, that should be 1.6. They round bad. They round no good. Alright. So, this was... Alright, let's learn how to do this on a calculator. I'll show you guys this in class as well. So, instead of doing it longhand, I could have done this. I go to my distribution, second bars. In this one, I'm plugging in NPK. N is the number of trials, P is the probability of success, and K is how many successes we're looking for. So for the original problem, I would have done, that was when K equals 3, when X equals 3. I would have done 5 trials, 0.25 chance of type O. I'm looking for 3. Same thing. For greater than 3, I could have done the complement. CDF means cumulative. PDF gives you 1 value. CDF gives you from 3 on down. So think about this. When I did binom CDF, what I'm actually finding is the probability that X is less than or equal to 3. So that means 0, 1, 2, and 3. If I subtract that from 1, I'll get the probability 4 and 5. Which we did. We'll go through this more in class. This is an intro. Make sure you know how to do it both ways. Alright? And that's where we'll end it. Have a great day, guys.